The rate of a reaction is determined by its mechanism and rate constant. Thus, to change the rate of a reaction, the first way is to change the reaction mechanism using catalysts. We will discuss this topic in the next section. The second way is to change the rate constant by changing the temperature. It is well known that chemical reactions are accelerated at higher temperature. For example, at room temperature, magnesium is stable in air. But once it is ignited, it burns violently. Experiments proved that the rate constant, rather than the mechanism of the reaction, changes with temperature. For example, the decomposition of acetaldehyde has a fixed rate law between 700 and 1000 Kelvin. The rate constants at different temperatures in this range are shown in the table. A dramatic increase of rate constant with temperature can be found. Furthermore, there is a linear relationship between log K over K0 and the reciprocal of temperature. Here, K0 is an arbitrary constant with the same dimension as the rate constant, so that K over K0 is a pure number. The relationship between the rate constant and temperature can be formulated with such equation. A and B are constants related to the reaction, which can be found by linear fitting. A more widely used form of the previous equation is called Arrhenius equation. In the Arrhenius equation, EA is called activation energy. A is called pre-exponential factor. Both of them are constants. The physical meanings of them will be discussed later. The activation energy can be found by the linear fitting of log K over K0 versus the reciprocal of temperature. In the previous example, the activation energy of the decomposition of acetaldehyde is about 195 kJ per mole. Molecular collision theory can explain rate constant's temperature dependence for bimolecular reactions in gas phase. In molecular collision theory, the reactant particles collide with each other randomly. But only collisions with enough energy lead to successful reaction. To further simplify the model, we suppose that the reactant particles are hard spheres with certain radii. Consider the collision between two particles with radii Ra and Rb. When they travel, they collide if their distance falls below Ra plus Rb. Here, the condition of collision has nothing to do with the individual radii, but the sum of them, d. Thus, this condition is identical to the system with one particle with 0 radius and the other with a radius of d. Moreover, the collision frequency and energy between two traveling particles depends on their relative velocity rather than the individual velocities. The relative velocity of two traveling particles is identical to that of one stationary particle and one traveling particle with the relative velocity, upsilon. So, when calculating the frequency of collision between two particles, the system can be replaced by a stationary point and a particle with radius d traveling in velocity upsilon. When a sphere travels in space, it sweeps out a cylinder. The volume of the cylinder is equal to its cross-section multiplied by its length. The cross-section of the cylinder with radius d is called the cross-section of collision. The length is the distance traveled by the sphere. The number of collisions between the particles is the number of times when the traveling sphere contains the stationary point. It is the ratio of the volume of the cylinder to the volume of the space. The collision frequency is the number of collisions per unit time. The molar concentration of collision frequency between two species of particles is the collision frequency between two particles multiplied by the numbers of particles in both species, and divided by Avogadro constant and the volume of the space. Here, the number of one species of particles is the product of its concentration, volume, and Avogadro constant. Meanwhile, the relative speed between two particles is replaced by the mean relative speed between two species of particles. The relative velocity between two particles depends on the angle between their velocities. Since the particles travel in arbitrary directions, the mean angle is 90 degrees. Thus, the mean relative speed can be calculated with Pythagorean theorem using the mean speed of the particles. Here, the mean speed of a particle in ideal gas is given by the Boltzmann-Maxwell distribution. The mean relative speed depends on temperature and the masses of the particles. To simplify the expression of mean relative speed, define the reduced mass. Then, the mean relative speed has the same form as the mean speed of a species of particles. Finally, we have got the expression of the molar concentration of collision frequency between two species of particles. For example, let's calculate the collision frequency between hydrogen and ethylene molecules. First, calculate the collision cross-section in hard sphere model. Second, calculate the reduced mass. Insert the results to the equation for collision frequency. On the other hand, experiments show that the rate of reaction between hydrogen and ethylene in the same condition is much smaller. It is because most of the collisions have insufficient energy and are inactive for the reaction. Only collisions with enough energy lead to successful reaction. Active collisions are the collision whose energies are greater than a minimum molar energy, E0. Statistical mechanics shows that the fraction of active collisions is a Boltzmann factor. It is e to the power of minus E0 over RT. Now, we can consider the rate constant. It is the molar concentration of active collision frequency divided by the concentrations of A and B. The result is in terms of the microscopic properties of reactants. The rate constant from collision theory is close to Arrhenius equation. However, the pre-exponential factor is not a constant, but is proportional to the square root of temperature. The activation energy is not a constant either, but E0 plus half RT. In most cases, E0 is much greater than RT. Thus, activation energy is approximately the minimum collision energy required for the reaction to occur. The collision theory successfully predicts the activation energy, but usually overestimate the pre-exponential factor by a large margin. The ratio between observed and calculated pre-exponential factors is called the steric factor. Here, I show you two examples, in which the steric vectors are much smaller than 1. A tiny steric factor is the result of non-spherically symmetric reactant particles. Thus, only the collisions from the right directions lead to successful reaction. For example, the reaction between ethylene and hydrogen occurs only when the hydrogen molecules collide with the ethylene molecules' double bonds. Collisions between the hydrogen molecules and the hydrogen ends of the ethylene molecules do not lead to reaction. Another theory to explain the temperature dependence of rate constant is transition state theory. It focuses on the relationship between chemical kinetics and equilibrium. The transition state theory is inspired by the similarity between the temperature dependencies of rate constant and equilibrium constant. The latter is known as Van't Hoff equation. So, the activation energy should play the role of the enthalpy of a reaction in equilibrium. In transition state theory, reactants form a transition state in the first step, which then converts to product in the second step. The transition state is also called active complex. Furthermore, transition state theory assumes a special type of chemical equilibrium, quasi-equilibrium, between the reactants and the transition state. The reaction mechanism in transition state theory can be summarized with the following formula. Here, T double dagger is the transition state. The equilibrium constant of the first step is uppercase K double dagger. According to thermodynamics, this equilibrium constant can be calculated from the Gibbs free energy of activation. The Gibbs free energy of activation is further expressed in terms of enthalpy and entropy of activation. The transition state then converts to the product in a unimolecular reaction. The rate of the overall reaction is the product of the concentration of the transition state and the rate constant of the second step. The rate constant of the second step is the vibrational frequency of the transition state. Classical theory suggests that vibrational frequency is proportional to temperature. Combining the expressions of the vibrational frequency and the concentration of the transition state yields the rate of the overall reaction. The expression of rate constant here is called Eyring equation. It has a similar form as the Arrhenius equation, but the pre-exponential factor is proportional to temperature. Collision theory and transition state theory are closely related. Consider a simple reaction, in which atom A and molecule BC react to form molecule AB and atom C. When A and BC approach each other, the potential energy increases due to Pauli exclusion principle. However, when they get close enough, a new complex is formed, and the energy reaches a maximum. The complex is active because of its high energy. Meanwhile, some of active complex dissociates to return to the reactants. So, there is a quasi-equilibrium between the reactants and the active complex, that is, the transition state. The energy difference between the transition state and the reactants is called the energy barrier of the reaction, which is approximately the activation energy. It is also approximately the enthalpy of activation in transition state theory and the minimum collision energy in collision theory.